So now we move on to the derivatives of carboxylic acids, and as usual, we'll start with the nomenclature, properties, and some applications. So first of all, the derivatives of carboxylic acids. Here they are all acyl chloride, acid anhydride, carboxylic ester, amide, and nitrile. Nitrile is a little bit different because it has no carbonyl, right? We talked about this, but otherwise all of the other ones, they have an acyl group. An acyl group is this kind, okay, where you have an R group that's connected to a carbonyl. That's called an acyl group. So you can see all of the ones here in blue, that's the acyl group. And so all of the derivatives have it except for nitrile, but nitriles are still considered to be the derivatives of carboxylic acids. They belong to the same family because you can convert the nitriles into any of the derivatives. And actually that's the whole point of derivatives, is you can convert one into the other. Okay, so aldehydes and ketones, for example, I would never call them derivatives because they're not. You can't convert one to the other, but all of these you can convert one to the other. Okay, that's why they're called derivatives. Okay, so we'll go through these one by one, and the nomenclature for some of them is just quite brief, and for some it's a little bit long. Okay, so for acyl chlorides it's a little bit brief, but anyhow, so here what do? Is we take whatever acid we have, okay, so the ic acid, so whether it is ethanoic acid or formic acid, and then you convert it to il chloride. Okay, so for example, the first one with the carbon here, that's called methanoyl chloride. Second one is ethanoyl, and again I've given you the general names as well. So formoyl chloride, acetyl chloride, and then here is the one from benzoic acid called benzoyl chloride. Okay, so don't try to make it too complicated, just keep it simple and convert to il. Okay, so just simple stuff. The properties of all of these, what I'm going to do is take them a little briefly, because a lot of these actually are not very stable compounds. They're very reactive. So their properties, it's like there's no point talking about them because nobody really works with them outside the lab, okay, per se, because they don't occur naturally. So for example, for acyl chlorides, they're all soluble in water, not because they are dissolving in water, but because they are reacting with water. Okay, and so what we are going to do later on is learn about their synthesis, how to make them, and then what kind of reactions they do. So you will learn a little bit about all of these, okay, when we go on to the reactions part. But really they are very reactive, they are toxic, and of course they are foul smelling. And I think I can see a little bit of an error over here for spelling. So they are foul smelling, okay, not selling. They don't sell anything foul. I mean, they could because they stink. Okay, so that's acyl chlorides. Then anhydrides are kind of similar to acyl chlorides in the sense that they're a derivative of carboxylic acids, and this is what they would look like. So there's a carbonyl which are connected by an oxygen. There are a lot of oxygens here, okay, so you have to be careful and you have to be able to tell them apart. So for example, when we deal with aldehydes and ketones, we had the acetals, we have peracids, and now we have all of these carboxylic acid derivatives. You really need to learn them, okay, and tell them apart. So this just takes practice. All right, so just kind of keep seeing them and then learn to recognize them. So here is an anhydride. An anhydride can be anything with two carboxylic acids, but you don't see the two acids. But what you will see is three carbons separated by, or I should say, two carbonyls separated by an oxygen, or connected by an oxygen. That's an anhydride. Okay, an anhydride means something that is without water. Anhydrides are generally going to be internal groups, okay, so they are found between carbons, And what internal group means that is you can find them in a ring also. Like acyl chlorides, those are terminal groups. You only find them at the end. But carboxylic anhydrides, you can find them in a ring as well. Okay, so for example, something like this. Now look at the name here. Okay, so this is succinic anhydride. This is coming from succinic acid. And if you're wondering where is the acid, I don't see the acid. And that's because we haven't done the synthesis or anything yet, right? But I'm going to show you really quickly how that works. And so here, if you cleave this, here is the acid, and then here is the other OH. So here is the acid, and here is the acid. So succinic acid will give us succinic anhydride. Okay, maleic acid will give us maleic anhydride. So again, even if you cleave here, it doesn't matter because here is the OH and then here is the OH for this carboxylic acid. The same thing happens if you have something like this. So really what you're adding is OH, right? So adding the water right back, and hydride means without water, and then adding water will give you the acids back. Okay, that's kind of how it works. Again, don't worry about the synthesis yet. We will talk about all of that, but it's just to help you recognize the acids and the anhydrides there. Okay. The anhydride nomenclature is, again, we'll just do the simple ones: acetic anhydride, formal anhydride, or the methanoic anhydride. I mean, there's really not much that I give you to name with anhydrides, okay, but their name ends with anhydride, so you kind of know that you're dealing with anhydrides, okay. The properties of anhydride are very similar to acyl chlorides, which means that they react with water, so they are soluble in water, they are reactive, and they're toxic, and again, they're selling foul. Oh my God. Okay, so I was just copying and pasting, wasn't I? Okay, so foul smelling compounds over there. Okay, so let's move on. Carboxylic esters. Now, carboxylic esters you have learned as a functional group because these are stable now. Okay, so this one we really have to talk about as far as nomenclature is concerned because they're very stable compounds. You find them in nature everywhere. So anyhow, first of all, carboxylic esters, all the names will end in ate. Okay, and you might remember we did the nomenclature for uh, carboxylate salts, which is like the acid plus base gives you the salt and water, right? So the acid, carboxylic acids, when you react them with base gives you carboxylate. And so everything ends in ate. So carboxylic esters also will end in ate. Okay, and the thing about the esters is they're actually made from an alcohol and they're made from an acid. So if they're made from an acid and an alcohol, the alcohol is the base. Okay, so let me show you again how this really works so you kind of understand this, although we will learn this again, but this is kind of how it works. Okay, so again, if you cleave over here, you get the OH here and the H here. So here is the alcohol and here is the acid, okay, part. So the alcohol part right here, this is kind of the base part, and then here this is the acid. And because this is an acid-base reaction, you end everything in ate. Okay, so as soon as you hear that something is an ate, it's a salt. So if it's a salt, well, then this carboxylic acid is an acid. Where is my base? Okay, the base is alcohol here. Anyhow, once you know this, then you kind of know what to look for. So the carbonyl group is going to belong to the acid, whereas the oxygen group is going to belong to the alcohol. Okay, whatever belongs to the alcohol or to this oxygen, that's what you're going to name first. So I've highlighted it here for you. So all the yellows, okay, those are what you would name first because that's what's connected to the oxygen. Whatever is attached to the carbonyl, that's your base name. Okay, that's the base for the carboxylic acid. So that is how you will name carboxylic esters. So the first one here is the methyl and then methanoate. Okay, so let me go ahead and erase all of this so you can actually see. So here we go. Okay, that's the base, which is only one carbon, so that's going to be methanoate, and then the methyl group here, methyl methanoate, methyl formate, that would be the IUPAC name. Okay, so then ethyl and then ethanoate. So again, two carbons is ethanoic acid, so ethanoate coming from there, and then this would be ethyl acetate, sorry, not methyl. So I'm finding some errors here, but this is easy correct here. Okay, so ethyl acetate, that's what it's going to be. So then, you know, that's how you would name these things. Okay, again, in the next one I've highlighted it for you, isopropyl butanoate. I mean, after a while you start going IUPAC. Okay, so the methyl acetate is a general name, but then an isopropyl butanoate, just stick to the IUPAC. That's a lot simpler. Okay, here is methyl benzoate. So methyl group is here and the benzoate is from here. And then phenyl ethanoate. So phenyl is the group that's attached to the oxygen, and then ethanoate is the base. Okay, that's the parent chain for the carboxylic acid. Okay, so don't be fooled. There is no one way to draw an ester to say that you have to draw the carbonyl first or the carbonyl afterwards. So there is no set way of drawing it. So you kind of have to just identify, okay, where the ester is, and then identify what the base chain is going to be. Esters are internal groups. Okay, so I've drawn some here for you. For the cyclic compounds, a cyclic ester is called a lactone, and these lactones are defined by how many carbons there are. Okay, so the carbonyl carbon is right here. This is the oxygen, this is the carbon. Okay, that makes the ester. So that's the ester group. And the way this lactone is defined is by how many carbons are between the carbonyl and the oxygen. So alpha, beta, this is a beta lactone, this is a gamma lactone. Okay, there is more nomenclature, but we don't have to do it right now. Okay, so those are your esters. Regarding the properties of carboxylic esters, because now these are stable groups, so let's talk about that. The melting point, boiling points, they're a little bit lower than carboxylic acids because there is no hydrogen bonding, but there is dipole moment, there is some polarity. So it is high but not high. Okay, like it's low, but they're liquids. Okay, still they're liquids, they're not gases or anything. All right, because of the dipole moment. They're generally not going to be soluble in water because again there is no hydrogen bonding. If there is any slight solubility, it's because of the dipole moment, you know, or the dipole forces, but otherwise really not soluble in water. And then the odor. By the way, the density of these ones is generally going to be lower than water, but it can depend on the molecular weight. Okay, so I didn't write it. Odor is really one of the best things about carboxylic esters. So until now, we've been talking about the derivatives being stinky, 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 you know, foul smelling and whatnot. But this one is actually really, really beautiful smells. They're fruity smells. So whether you're smelling apples or bananas or peaches, these are all actually going to be carboxylic esters. So here are the applications. So I've given you some of the esters and the, you know, the fruits associated with it. So banana, for example, and amyl acetate, we used to make this in our lab, and then yeah, the whole lab would smell of bananas. A little overwhelming, you know, but it does smell like banana, you know. Wintergreen is probably one of the best smells that, you know, that you can do in the lab because it smells amazing. Then, you know, there are some other of these smells that you can get from the ester. So like, you know, when manufacturers make candy or, you know, juices, fruit juices, they're not really adding fruit juices. They just take, you know, they just synthesize these esters and they add them, and that's why, you know, it will never taste the same when you take something that is natural, you know, natural orange versus a flavor. It's they're not the same things. Okay, because a natural thing has a lot of other flavors with it too that make it different. Okay, so you can have these artificial flavors, but it does not really make up for the natural flavors. Okay, but they're there at least. Esters are also very good solvents because they are very unreactive. So ethyl acetate, for example, is a good solvent to work with. So, you know, in the lab we use them a lot. Then another application is polyesters. And so polyester is when you take an ester and you make polymers of that. So you take many alcohols and, you know, diols and diacids, and you combine them. And polyester is like one of the best kind of cloth out there, right? To you don't have to iron anything. It cleans nicely. It lasts forever. So that's, you know, clothing stuff, and also can used in plastic bottles. And, you know, I mean, all of these things, these are in a way terrible because they don't really degrade in the environment. So environmentally not very good. but they do last a long time, so that's polyesters. Aspirin is an ester, so right here is the structure of aspirin. Bayer was the first company to synthesize aspirin. I think that was like 1895 or something. So it's been around for a long time, and it's one of those drugs that is used really universally, or globally, I should say, not universally, okay, but globally. Then here is the structure of vitamin C, which is a lactone. Right here you can see the ester, and vitamin C, of course, for us, you know that we need vitamin C. It's an essential vitamin for us. And then a lot of enzymes in our body. Okay, so you can see like esters are everywhere. Okay, you cannot escape esters in your life. All right, so then amides, okay, the next functional group, and amides are also very stable. That's why you learn about amides as a functional group initially. And here what you have is a carbonyl, and then here with the nitrogen attached to it, okay? Those two hydrogens can be two hydrogens, or they can be any other alkyl group also, okay? But otherwise, generally, there are two hydrogens, but that's an amide. So you can see there is only one oxygen, and that oxygen is the carbonyl oxygen. There is no other oxygen in there, okay? Like acyl chloride had also one oxygen, and hydride had three oxygen. Esters has two. Now amides has one, just the carbonyl, okay? Just the acyl group. So that's going to be the amide functional group. Now the naming, as far as the naming is concerned, again, you have to give the base name to the carbonyl carbon. So this one here for the first one, this is called methanamide. The general name for it is formamide. Form coming from the one carbon, and then amide, okay? And then methanamide, easy enough. Methan, just remove the E, put the amide, and you're done, okay? Ethanamide, butanamide, pentanamide, so on and so forth. They can go on. Now, you can also have substituents on the nitrogen. So if that happens, then you have to say the substituent as N, whatever substituent, and then the base name, okay? So in this case, N-ethyl ethanamide, okay? Here is the structure of benzanamide. Benzanamide coming from benzoic acid. Remember, this is the base, okay? So which means base, meaning the base name. So here's the carbonyl with the benzene ring. So that's going to be the benzoic acid, and then amide, okay, over here. If you have two groups on the nitrogen, then you have to name both of them, okay? So NN, you have to say it twice, even though they're the same. So NN dimethyl butanamide, 1, 2, 3, 4. So butanamide is the chain there. Now, if you had two different groups here, like it was an ethyl and a methyl, again, just go alphabetically, okay? So N-ethyl and methyl butanamide, or whatever it is. So that's amides. Now, amides can be internal groups because you can see they're surrounded by carbons. So just like lactones, amides are called lactams. Okay, so they have a very specific name. And the reason these things get specific names is because you find them everywhere. Okay, that's why you can give them specific names. So this is a lactam, and lactam is like this. The nomenclature is very similar to what we did for lactone, which is the number of carbons that connect the nitrogen and the carbonyl. So alpha, beta, beta lactam, gamma lactam. Okay, and that's all we have to know. Even if you don't know lactam, I'm totally fine. Know at least that it's a cyclic amide. Okay, that much you must know. So that's it, I think, for amides. Let's talk properties. So the properties, melting point, boiling point is going to be really high because nitrogen compounds have hydrogen bonding. Okay, so again, it depends on what kind of substituents you have on nitrogen. So I can't say generically that it's going to be high. It's going to be high, but then it also depends on what is on the nitrogen. Okay, so you have to watch out for that when you're comparing the boiling points and melting points. The solubility in water again depends on what is on the nitrogen. If there's only hydrogens, then the small amides will be soluble because of hydrogen bonding. But if you have alkyl groups on the nitrogen, then no. Okay, they're not going to be soluble in water. So that's how it's going to be. Amides generally don't have any odor. Okay, and we will talk about amides also when we go on, but amides are kind of also like salts, but these salts, they here the amine is the base. Okay, remember we were talking about esters just now. In esters, the acid was the acid, and then alcohol was the base. Here in this case the acid is the acid, but the base here is going to be the amine. Okay, whatever nitrogen group you use, that's going to be the base. Okay, so they don't have any odor generally. That's why they have high boiling points too. Well, not okay, that's not all that related with it, but anyhow. Okay, so applications of amides. Amides are found almost everywhere also. So in pharmaceuticals, for example, you can find them a lot. So a lot of the antibiotics, okay, like this one here, I've given you the structure of penicillin. The antibiotics are usually made up of lactams, which is a cyclic amide right here. It's very common. Okay, and then here this is the structure of acetaminophen, which is Tylenol. All right, so you can see very common for us. And then here are plastics again. Amides, polyamides are also used a lot. Okay, like nylon and all, they're used a lot in polymers, and they're very strong compounds. Kevlar, as you know, which is the bulletproof vest, you know, that police and everyone wears. Not everyone, but police and law enforcement wears. That's, you know, made of amides, which is really very strong and protects them very well. So really strong there. Amides, they can be used as solvents. There are a few of them that are used as solvents. Dimethylformamide. Again, formamide means that you only have one carbonyl and or one carbon, that's it. And the nitrogen has the two methyl groups. Okay, so dimethylformamide, then dimethylacetamide. These are very good polar solvents. So depending on what kind of reaction you are doing, if you need something with a high boiling point, then these are very good solvents for those. And finally, nitriles. I call the nitriles like the stepchild in this because, you know, they look very different. They're not the same as like the black sheep of the family. You know, they have no carbonyl, but they are kind of counted as a carboxylic acid derivative. But, you know, that's all right. We can live with that, right? So in any case, their nomenclature is very straightforward. As you can see, methane nitrile, ethane nitrile with two carbons. Now, if you had this in inorganic chemistry, you would probably call it hydrogen cyanide, right? HCN. But in organic chemistry, because we are focusing on the carbon and the number of carbons, so that's methane nitrile. So we're looking at this cyanide as actually a nitrile group, okay? Ethane nitrile, benzonitrile, very straightforward. Nitriles are going to be all very reactive, and they're all water sensitive. So that's why, like initially when you know, learning functional groups, you don't learn about nitriles because they're very reactive. All right. So here are all the derivatives, and all of them on one slide here for you. So feel free to go through it. Let me know if you have any questions. I don't think I have anything more to say about any of these. Yep, it seems like we're done.